Hey everyone, in this video we're going to focus on how to do titration calculations, which in essence means determining the concentration of an unknown either acid or base by titrating it against a known concentration of acid or base. All of these reactions are acid-base neutralization reactions, where in general we follow the paradigm of acid plus base gives us water and a salt. And by a salt, it's an ionic compound. When we read the problem in front of us, what is the concentration of a 15 ml sample of a sulfuric acid solution that is titrated with a 0.150 molar solution of potassium hydroxide if 22 milliliters of the base were needed to reach the end point of the titration? The first thing we need to do is write out the balanced chemical equation. Now, the AP exam may or may not specify how they want you to do this. If they wanted you to write if they don't give any instruction, generally you're fine then with just writing the molecular equation. And in our case, we have H2SO4, sulfuric acid, and KOH, giving us, here is where the hydroxide combines with the protons on the acid to make water. One of the things you'll notice, though, of course, is that with sulfuric acid, there's 2 protons, so therefore, we're going to need 2 moles of base, or 2 equivalents of base, in order to make 2 waters and our salt. And if potassium is +1, hydroxide is -1, hydrogen +1, sulfate is 2-, we can't just simply make KSO4, but instead we need 2 of these potassiums to balance the 2- of the sulfate. This is how you would write the molecular equation. You may, however, be asked to write the net ionic equation. And in this case, it's a little different than what you might expect. Because sulfuric acid is strong, technically, only one of those protons, and this is just something that you have to know, only one of these protons is actually strong, and the other is considered a weak proton. So, in a case like this, if we were writing this as a net ionic equation, we would have to write 1 proton on, 1 proton off, because this is the physical reality of sulfuric acid in water. One of those protons comes off and bonds with the water as a hydronium ion. Now, in the case of potassium hydroxide, KOH +1, -1 is going to be completely soluble. And because of this, the potassium is going to be a spectator ion, because with the sulfate here, it's not going to precipitate, because as a +1 to negative, all group 1s are essentially not going to precipitate. They're essentially soluble. So we're not going to include the potassium because it's going to end up being a spectator ion. If you went ahead and write potassium right now, K plus, as its own thing, that's fine too. We'll just cancel it later. So now we make 2 waters. So if we remove that second proton, because water is not strong enough to remove this, but hydroxide ions are. Hydroxides are a much stronger base. We then write SO4 2- as our resulting ion. And it is not a spectator ion because it's in fact different on the 2 different sides of the equation. On the left-hand side, we're bonded with a hydrogen. On the right-hand side, we are not. So therefore, because the species changes, it does get included in the net ionic equation. So now we have essentially the 2 equations telling us the same exact thing. What we really need to understand, though, is that 2 moles of base are required to neutralize our acid. And this is going to matter later on. If we were using something as simple as hydrogen chloride or hydrochloric acid, HCl, with only 1 proton, we would only need 1-to-1 or 1 equivalent of base. But because H2SO4 has 2, we'll need 2 equivalents of base. Now we're told that the end point is reached at 22 milliliters. I'm going to make a quick sketch of this just so that it's visual and you can see what we're looking at. If you have your solution of the H2SO4 below, and we're titrating in the base, KOH, what we're told is that we have 15 mils here, and we have 22, I believe is what it said. Yep, 22 mils of the base is added. If we were to draw a titration curve, what we would see here is that it would look something like this as a titration. We would have an inflection point of 7 where the midpoint jumps here because this is a strong acid and base. And if we follow this down according to the problem, this milliliters at the equivalence point is the 22.0 of our base added. So let's scroll back up and take a look at this problem. And do some calculations. When we write our math out, we're going to start with the base. It's the thing that we know most about. And of course, because molarity means moles per liter, we're going to start out with 0.150 moles of base per 1 liter. And here's where we're going to use the amount added. If I multiply by 0.0220 liters, what I'm in effect doing is determining the moles of base added. And according to my balanced chemical equation, 1 mole of H2SO4 is neutralized by 2 moles of hydroxide. Again, using the diagonal rule, leaving the 2 on the bottom and dividing by 2, what I'm doing is I'm now converting the moles of base added to the moles of acid that must have been there at the point of titration, or in totality. And if I stopped here, my label would be moles of acid. So if the question was asking me how many moles of acid were in the flask below, I'd stop and calculate. But that's not what this is ultimately asking. This question wants to know the molarity of the acid. And here is where I'm going to divide by the sample size of my acid. And with 0.0150 liters, 15 mils of acid, here is where I'm now going to have moles per liter as my final unit. Taking out your calculator, you're going to enter 0.150 times 0.0220 divided by 2 divided by 0.0150, and what we're going to end with is 0.110 to 3 sig figs molar H2SO4 solution. This is the most common type of calculation you'll have to do with titration. Something else that you may have to do is you could answer the question, what grams of H2SO4 were below? We already mentioned how if we had stopped here, we would have ended up with the moles of sulfuric acid. If you wanted to know how many grams there were, you would simply stop there and then use the molar mass, right, the grams per mole, of sulfuric acid and apply it to those moles. That's it for now, folks. Liters.